Hello, everyone. Thank you for joining us today for our ALS Webinar Wednesday series. My name is Malia Forbes, a marketing coordinator for ALS North America, and I'll be facilitating the webinar today. Our presenter today is Nicole Bryson. Nicole completed her undergraduate degree in chemistry at St. Lawrence University and afterward worked as an analytical chemist in the pharmaceutical industry. In 2000, Nicole completed her MBA in marketing from Pace University in White Plains, New York. She has been working in the environmental industry for the last 15 years and has specialized in air and vapor sampling and analytical methodologies for more than 10 years. Nicole is now the technical sales manager for the ALS laboratory in Simi Valley, California. Nicole, thank you for taking the time to deliver this presentation. I will now turn it over to you.
Thanks, Malia, and thank you everyone for joining us. Today we're going to talk about things you'd like to know about TO-15. Here's a quick overview of the ALS laboratories in the United States. I work for the laboratory in Southern California in Simi Valley. So we're going to talk today about some of the top questions that we get about TO-15 and sampling and analysis for air and vapor in general. And I think the number one question that we get is, why don't you have any cans? So this question depends on really a number of factors. The first thing is a canister inventory. I think many people in this practice area have had the experience where they want to do a sampling event and they call their lab and they don't have any cans available. So why is that? Well, first, it depends on how many canisters does the laboratory have in their inventory to start with. Our laboratory in Southern California has about 3,000 canisters. That makes it probably one of the largest single location inventories in the United States. So we have a lot of cans. Once you get past the inventory, what else can determine canister availability? Well, time of year plays a big factor. In air and vapor testing, there's definitely some seasonality to canister demand. I think that there must be a day in March that's on everyone's calendars that is Order Your Canisters Day, because I think every consultant in America all of a sudden decides to do their indoor air testing the same last few weeks in March to get in their indoor air testing for the winter. The seasonality is partly a function of vapor intrusion investigations, where you often want to have a winter sample and a summer sample. So winter can be slower, but then in February and March, as everyone wants to get their samples done for that time frame, can get really busy. For example, we can ship more than 500 canisters per week in March. Another time of year when it gets very busy is actually the summertime, when people are also doing their summer samples for indoor air. So there can definitely be periods of peak demand. So when you have events during those time frames, it's very helpful to keep that in mind and try to give more advance notice if you can. What else impacts canister availability? Well, a big factor is, how are you QCing the canisters? Are you getting batch certification or individual certification? This picture is of our canisters in an oven, and this relates to the cleaning and QC process. So here's an oven that has, looks like 9 or 10 canisters in it. And in a batch QC process, the canisters are cleaned via ovens like this, where they're heated and purged, filled and evacuated numerous times so that they can be cleaned of the volatiles in them. In a batch certification process, one canister then from that batch is selected and a full TO-15 analysis is run on it. At our laboratory, you can see these tags. Here are the tags for the canisters, and we write on them what the highest concentration contaminant is for that canister. So then when it's time to do the batch QC, we select the canister from that batch that had the highest concentration of contaminants, the dirtiest can. We run a TO-15 analysis on that canister, and since that was the dirtiest one, if that comes back clean with no hits, then the whole batch is presumed to be clean. This applies to batches of up to 10 canisters. For individual QC, It's exactly what the name implies. It's individual analysis of every canister. So in this set of canisters, instead of just selecting the dirtiest one, every single one has to have a TO-15 analysis on it. This is very common for the canisters that are going to be used for indoor air testing, for risk assessments, and need to achieve super low reporting limits. So individual QC is done to ensure that the canisters really are clean at those very low reporting limits. Now, there's nothing about indoor air or even TO-15 sim that requires you to do individual QC. In theory, one could do batch QC of sim canisters. However, it's just standard practice to do an individual QC so that you have the extra assurance that those super low reporting limits, the canisters are clean, and any hits that you get from your sampling will truly be due to your sampling event. The other thing that can impact the canister availability is the lead time. So taking all of these things into consideration, how many cans does the lab have, the time of year, batch versus individual QC, this is not, a strictly numeric graph. I was just trying to demonstrate that the lead time really depends on what you're asking for. If you only need like one can and it's a batch QC can, you can get that pretty much almost next day most of the year. The more cans you need, the more lead time we need. If you need individual QC versus batch QC, we need more lead time. Typically for individual QC, since we do this QC to order on a custom basis, you usually need at least 3 to 5 business days for individual QC. And the more cans you need, the more lead time. So just keep that in mind as you're planning your events. We are doing everything we can to increase our capacity, increase our supply, to make this as easy as possible and support anything that you need. It's just there are rate limiting factors for canisters that you don't have when it comes to soil and water testing with bottles. Since the canisters cost $500 a piece, it's a little bit harder to order a whole bunch of new ones like you can for pallets of bottles or jars. So those are things you want to keep in mind when you're going to be ordering canisters. What do you need to know to place an order? Well, that depends. The laboratory likes to know, at our laboratory, what you're going to be testing. Are you doing indoor air, ambient air, soil gas subslab? We ask you that because at our laboratory, we separate our canisters based on application. So it helps us to know what you're going to be collecting. We do this to help ensure that we can deliver those squeaky clean canisters for indoor air sampling so that you can be ensured when you're doing super low reporting limits at SIM, you're getting clean canisters. Once canisters have been exposed to higher concentrations of contaminants, they get shifted over to applications for soil gas, subslab, landfill gas. The other thing we need to know to place an order is what are your target analytes? So that's a little bit different than, again, say soil and water sampling where you just get bottles and jars. We need to know what your target analyte list is so that we can properly QC the canisters. What does this mean? Well, if you were to order canisters and you have target analytes that we didn't check the canister for, when you do your sampling, if you were to then run it for analytes that we didn't QC it for, we wouldn't be able to say whether or not those analytes were present before your sampling event. So that's why it's so important that the laboratory knows what target list you want to be running it for so that we can properly QC the canisters. What else do we need to know? What are your reporting limits? Again, this goes to the QC. We need to know how we're going to do the QC to know if you need scan reporting limits or SIM. This isn't usually something that you as a customer have to decide whether it's scan or SIM, since it really depends on the laboratory how they're achieving those reporting limits. But we need to know so that we can give you the guidance on, okay, for this reporting limit, we need to run it this way. At our laboratory, typically, we can achieve reporting limits of 0.5 micrograms per cubic meter for a 6-liter canister by TO-15 scan. And for the lower reporting limits, we can achieve reporting limits of 0.025 micrograms per cubic meter by sim. Sim is usually only applicable for ambient air, indoor air, and it isn't relevant for soil gas. Generally, soil gas screening levels are high enough that they don't need sim reporting limits for us to achieve them. To place an order, we also need to know if you need batch or individual QC. And then if you're going to be using a flow regulator, we need to know what flow rate or time interval you need so that we can calibrate the flow controllers for you. These can't be adjusted in the field, so we need to know. So those are some things you need to have in order. What is another question we get a lot? Well, what's the difference between 6-liter and 1-liter canisters? In practice, there's no difference. They're stainless steel canisters. They're treated the same way in terms of how they're prepared. Assume a canister is a canister that's gone through a process that makes it inert or passive to chemical contaminants, and that is the SUMA process. That's why they're called SUMA canisters. Currently, the canisters are also undergoing another process called silanization. So it's now generally called a silanite canister. The silanite canisters are the ones that are more commonly used by laboratories now. The silanite makes them inert in addition to VOCs. It also makes them inert to sulfur-containing compounds. Otherwise, the functionality between a 6-liter and a 1-liter can is the same. At our laboratory, you can get lower reporting limits from a 6-liter can. We use a larger sample aliquot from a 6-liter can than we do from a 1-liter. We can use 1 liter from a 6 and 400 mils from a 1. So that means the reporting limits on average are about 2.5 times lower with a 6-liter canister. The 1-liter canisters are popular for soil gas applications or SVE systems. They are lighter, they're easier to deal with in the field, they fill up faster. Since they're smaller and lighter, they're cheaper to ship. So those are some of the considerations between 6-liter and 1-liter canisters. Next question. What's the standard list for TO-15? Well, there is no standard list for TO-15. Every laboratory has a different target analyte list. So why is that? Well, TO-15 does reference a list of 97 VOCs that are included in the Clean Air Act of 1990. So in the Clean Air Act, there's 189 hazardous air pollutants, or HAPs, and TO-15 references 97 of them, many of which are on the slide that we're looking at right now. However, these analytes are listed in TO-15 because they meet the boiling point or vapor pressure for VOCs, but it doesn't mean that they can actually be done by TO-15. Some of examples of things that are in TO-15 that can't really be done by TO-15 include phosgene, epichlorohydrin. I can see on the list behind here a whole bunch of aldehydes, and those typically aren't stable enough to be done to be sampled and analyzed by TO-15. So there is no list specified in EPA method TO-15. When you work with a laboratory, you want to ask them what their standard list is, or see if they can provide that to you, or provide to the laboratory what your target list is for your site or for your project. So you'll want to talk to them about that to make sure that it has everything that you need before you proceed with your sampling event. Now we have some questions about canister vacuums and pressures. So at the laboratory, before we send you the canisters, we clean and QC your canisters, and then we evacuate them to absolute vacuum. And then we let them sit for 24 hours at our laboratory, and then we check the vacuum again. That's a 24-hour leak check. So then when the canister is sent to you, we evacuate it again to make sure it's at full vacuum, and that's where it should be when it gets to you. So what happens if the starting vacuum is not all the way over at minus 30, minus 29, minus 28? What does that mean? Well, you'll want to check before you begin your vent and see where it is. If it's not all the way at vacuum, it depends really on the circumstances. If it's just a little bit less, like minus 29, That could be due to variations in just the gauge. These analog gauges are qualitative, they're not quantitative. So a little bit less than absolute vacuum might be all right. It also might be a function of altitude. We've seen projects where customers were sampling at significantly different higher elevations than our laboratory, which is essentially at sea level, and that can cause differences in the vacuum. And once a correction factor was applied, then it's okay. However, if you get the gauge and it's significantly less, like half full, that would suggest that the canister leaked in transit or something happened. You probably don't want to use that because now if it's half full, you wouldn't know what it was sampling, and it certainly wouldn't be representative of your sampling event. I do know that many of our customers have their own SOPs or their own guidelines on how much vacuum should be in the canister for them to be able to use it. There is no definitive answer in EPA TO-15 or any specific guidance from the manufacturers of the canisters. So there is some gray area in terms of what are you comfortable with it using. I think as long as it's pretty close to minus 30, minus 29, it's all right. But if it's significantly less, you probably don't want to use that canister. What happens if the ending vacuum is 0? So oftentimes, sampling is conducted and guidelines indicate that there should be some vacuum remaining in the canister. Why is that? That's typically recommended for time integrated samples if you're sampling for, say, 8 hours. So if you're sampling for 8 hours, you open up the canister, you leave, you come back at 8 hours. If there's still a little bit of vacuum in the canister, then you know that that canister has been sampling throughout the time frame that it was set up to sample for. If you were to come back at that 8-hour mark, though, and it was at 0, you wouldn't know when it got to 0. Did it get to 0 just moments before you got there? So it really did sample across the time frame that you want it to, and the sample is representative? Or did it go to 0 a couple hours ago, and then it's definitely not an 8-hour sample? So that's typically why you want a little vacuum remaining in a time integrated sample so that it shows that it really did sample across the time interval that you wanted, and it's going to be representative of the time frame you're trying to characterize. If you're taking something like an instantaneous sample or a grab sample, and you're right there and you open the valve, it sucks in the sample, and you close the valve, it's probably all right then for it to be at 0 because you just observed the entire sampling process, and it will be representative of what you're trying to do. So if the vacuum is at 0, if that's good or bad for, or what it might do for your sample, really depends on the application and what you're doing. What happens if the ending vacuum is significantly negative? We have had customers say, I had an 8-hour sample, I set it up, but I had to go back and turn it off early at 4 hours. Is my sample valid? Well, it's not a question of whether or not the sample is valid. It's a question of what is going to happen to your reporting limits. Why is that? That's because the canister not filling all the way is going to significantly impact the dilution factor that's going to be applied to your sample. When we get our canisters back at the laboratory after they're sampled, we pressurize them with a known quantity of gas, of diluent gas, usually ultra pure air, and then we record that volume, and we use that to calculate a dilution factor. This is the example here, and you can see that we take the initial pressure of the canister. So here we would record it in PSIG. As an example, we got the canister and it was at minus 2.9. Then we added this ultra pure air, and then it was pressurized to 3.5. Then we do this conversion factor to convert the PSIG to PSI, and this gives us the dilution factor. And then we apply this to the reporting limits of your canister. So here's an example of a report so that we can look specifically at how does this impact my reporting limits. So here's a couple things we're going to look at. We're going to look at here's the initial pressure of the canister, minus 1.79. This canister was pressurized to 5.88. So using that equation that we just looked at, the dilution factor of 1.59 is determined. So what that does to the reporting limit is that the reporting limit is multiplied by that dilution factor. We also look at what was the volume that was analyzed for this canister. This canister happens to be a bottle vac. It's a 1 liter bottle vac. So 0.4 liters were withdrawn from that sample to be analyzed. That would yield a reporting limit, starting reporting limit of 1.3 micrograms per cubic meter. So then to that 1.3 micrograms per cubic meter reporting limit, it's multiplied by 1.59, which is how we get the effective reporting limit of 2.1. So that is how the dilution factor impacts the sample reporting limits. And since the dilution factor is a function of the initial vacuum, that is why it matters what the vacuum is received at. So if your canister only sampled for half the sampling interval that you wanted it to, like 4 hours instead of 8, that canister is going to be half full. So at the laboratory, a lot more diluent gas is going to be added to it. The reporting limit is going to be affected because the dilution factor is going to be higher, and it's going to make your reporting limit go up. So that's why you want to sample for the interval that you plan to if you're trying to achieve particular reporting limits. Another question related to this would be, why aren't the reporting limits the same for every sample? So as we just discussed, what impacts reporting limits? The dilution factor, and also the volume analyzed. So in addition to, in our example here, in addition to the reporting limit, in addition to the dilution factor, it's a function of the volume analyzed. So if we have a sample that can get 0.4 liters analyzed, but there's another sample that has much higher concentration of contaminants, we might have to analyze a much smaller volume. So that smaller volume is also going to go into the reporting limit as well as the dilution factor. So in order for your samples to have all the same reporting limits, they'd have to have the same volume analyzed and the same dilution factor. So small variations in what the dilution factor is, the ending pressure and the volume analyzed will impact what the reporting limits are for your samples. So those are some of the common questions that we get. Thank you very much for joining us today. We'd love to hear your questions, so please call us or email us and let us know how we can support you on your next event. Thanks very much. Have a good day.
Thank you, Nicole. This webinar presentation has been recorded. We post our webinars on our ALS Global website and our ALS YouTube channel. I encourage you to find a wide range of video resources and past Webinar Wednesday presentations available there. Also, please follow our showcase page on LinkedIn as we post announcements and registration links to future webinars and other valuable resources and updates. Thank you for attending this ALS webinar today. Have a great day.